other questions? Okay, so let me then begin. So today we'll discuss the what I had mentioned last time, that we have so far studied fluctuations in the position space, but we want to see how to convert this to angular fluctuation. More precisely, what we have studied here is really in the momentum space, not in the position space, but we can always convert them back and forth by Fourier transform. And the analog of this for angular fluctuation is the LM space, right? Because you can choose a basis of functions of theta and phi as some linear combination of theta phi. So any function of theta and phi can be decomposed in this way, right? So this is the analog of the momentum space for angles. And you want to know how to convert from the positions, the momentum space fluctuation to the LM fluctuation. So let's suppose that chi of k is some scalar fluctuation. For tensor fluctuation, you have to do a little differently, but we'll see that later. Okay, right now, let's suppose that you have some scalar fluctuation chi of k. Okay, of something, of some physical variable. Okay, which could be like delta t over t, and whatever it is, okay, we know that this can be written as some function of k times r of k e star. Okay, because all fluctuations, all scalar fluctuations, okay, those four quantities that you saw, phi b, psi b, zeta, and r, okay, all of them are determined in terms of the fluctuation of r at the horizon exit. Okay, so any fluctuation you can write as some function of k, okay, which you have to do some work to calculate this function of k times this. Okay, if you are interested in r itself, then the f of k is identity, right? If you are interested in phi b, for example, then you have this 3/5 factor and so on. Okay. But it's the fact that it's determined in terms of r is true also for sub-horizon, right? This f of k will be more complicated because it will still be a function, some function multiplying this r of k, right? Because it's linear evolution, and different momentum don't mix, right? For each momentum, you have a separate linear equation. Okay. And I also write down the Fourier transform. Okay. And in this lecture, I'll use the same symbol for the moment, a function and its Fourier transform, but it should be clear from the argument, right? Otherwise, I could have written chi and then some chi tilde here, okay, but I'll just use the same symbol, chi of x, which is integral d cube k over 2 pi cube and now the point is that what you observe is, well, chi of x, of course, but the natural coordinate in which you should put this is in the spherical polar coordinates, right? Because we are sitting at some point and we are looking into the sky, right? And we look at a given value of r, right? That's the distance to the last scattering surface as a function of theta and phi. Okay, so whatever you see as chi of x, you want to convert this into the polar coordinates. So let's suppose that we write x as r cos theta, sorry, r sin theta cos phi, r sin theta sin phi, and cos theta as usual, r cos theta. And we are going to use a similar labeling for the momentum. We'll write this as k times sin theta k cos phi k, k sin theta k sin phi k, and cos. Okay, this theta k phi k are independent variables compared to theta phi. So in other words, what we are doing here is that we are transforming both x and k into the spherical polar coordinates. And I should say that the origin is here r equal to 0 is ours. So that's the one that is relevant for us. So the idea is that we want to construct chi of r theta phi starting from this chi of x. So now we are going to use this relation that e to the I k dot x is 4 pi some, this is an identity, no, T star is not the last scattering star, right? T star is the time at the horizon exit. Because you said everything that happens later is determined from that one constant, right? For the scalar modes, it's this one constant that is the value of r at the horizon exit, right? Starting from that, you have the differential equation you evolve, and you determine what these various quantities are at the time of last scattering.
So what's visible to me is from last scattering time.
Yes, indeed.
Chi is the same as exit value of chi. And
that is for r it is true, but for phi, for example, it's not true, right? Phi b at the last scattering time, phi b was 0 at the exit, right? But at the last scattering time, it has become this 3/5 r, right? So that all that is contained in this function f of k, right? That given any physical quantity that you want to calculate, right? What you have learned is that the only data that we need, right, is the value of r at the horizon exit, right? Because then the differential equations will tell you how to calculate it, right? As long as you have linear differential equations, right? The initial condition which is provided by this will determine everything.
This is not a property of what kind of dynamics. This is property of the fact that I have a linear system.
Exactly. Yeah. So the dynamics goes in F. Right. What?
When it decomposes like this, it's just linear.
Exactly. Yeah. Yeah. So there's nothing special about this, right? So this is always true as long as the linearity holds, right? And you have translation invariance so that different k's don't mix, right? Chi of k will be only determined by r of k. F of k is something that we know how to calculate it. For example, for these simple quantities like phi b, psi b, etc. Right? We haven't seen how to calculate it for delta t over t. Right? That's the most interesting one, but that we'll learn afterwards. But whatever it is clear that it will be some function times the initial condition, right? R at the horizon exit, right? That's all we are saying here. Okay, so this function will have to determine case by case, right? Depending on what you want to calculate. So this is just a mathematical identity, right? This you might have seen while you studied scattering theory, right? That's scattering in quantum mechanics. When you have a plane wave, right, you want to decompose it into the spherical wave, and this is the formula that one uses while doing that. JL is the Bessel function. Okay? This is a spherical Bessel function with argument kr. Okay, so this is a function of k vector as well as x vector. The right hand side is also a function of the k vector and x vector, because you see theta phi is there, theta k phi k is there, k and r are there.
It's multiplying. YLM.
Multiplying, yes, multiplying. This just sum continues. So the idea is that we will substitute it in this expression over here. So chi of r theta phi will be given by integral d cube k over 2 pi cube times this whole sum, okay, which are not right. Okay, this whole thing. This goes here. But I can reorganize this by saying that this is sum over Lm chi Lm times ylm theta phi. Where now chi Lm is given by integral d cube k or 2 pi cube Is this clear? Okay, so this is chi Lm. Okay. So what we say is that if we know how to, if we know this, right? What we know is that, of course, a two-point function of this, but that we'll see in a few minutes. Okay. That knowledge of this can be used to determine chi Lm. And this chi Lm is something that we can directly experimentally measure, right? Because chi Lm is just integral. Chi Lm is integral d theta d phi, or sin theta d theta d phi. There is probably some normalization factor somewhere, right? But it's just multiply this by ylm, yl prime star and integrate, right? Because ylm has the orthonormality property delta l prime delta m prime. So chi lm can be directly determined in terms of chi r theta phi, and that this is what you observe, right? Chi r theta phi is, you look in some direction in the sky, the fluctuation that you see is chi r theta phi. Is this point clear?
Fluctuation from all across the spectrum.
Yes, exactly. Right. So to calculate chi Lm, we need fluctuations from all across the sky. Indeed. Yeah, we have. If you look at the CMB map, we have everywhere, right? Except that band where the Milky Way is there, right? But otherwise, you have most of the data. because you look everywhere, right? The space telescopes look everywhere. Okay, so I'm going to write down the expression for this quantity chi lm chi l prime n prime chi lm k. Let me write this as k prime well, I shouldn't say k here because k has gone, so chi lm star. This 2-point function. Yes.
R is going with that. So when you wrote chi lm, it was integrated over k f k r.
Yes.
But then I have this jl of k r, small r.
Exactly. Yes.
That is the radial size. That's going with that dependence is there in chi lm.
This one, yeah, because yeah, chi lm is implicitly function of r, but that is fixed because you are looking at large scattering surface.
So I have set r to what?
RLS, right? The co-moving radius of the large scattering surface. Right? If you are trying to calculate this at the large scattering surface. Okay, so that's why our information is not too relevant for us because we cannot look at different R, right? What the CMB comes from that specific R, right, which is a large scattering surface.
And I will also set T star equal to exit time.
Yeah, T star is the horizon exit time, right? So this is something that you calculate from inflation. Right? This sets the initial condition. And everything is determined in terms of this single quantity. Right? This of course depends on K, right? So it's a function of K, but otherwise for a fixed K, it's a single quantity that determines everything that happens in the future. Right? And now we are trying to calculate the 2-point function. Right? So whatever calculation, so the hard part of the calculation is already done. Right? Well, part of it is left because you have not calculated f of k for delta t over t, right? That you have to do. But that's the evolution of the perturbation. Now the question is that given this, how to relate it to the observation, right? Because what you observe is not chi of k directly, right? But angular fluctuation, right? You calculate the 2-point function, but in the angular coordinates, right? So we just have to translate what the fluctuations we have calculated in the momentum space to the LM space. Right? That's all we are doing here. Yeah, this is in essence basically kinematics, right? And the dynamics is already there in determining this f of k. Right? Now we are just trying to change coordinates.
I have one question. So about observation. So when I observe chi that is coming from the last scattering surface, and it has some value at T star, it is going to also undergo all of this cosmic medium, and it's going to undergo redshift.
All those that has to be taken into account. Right? So when you write a code, right, you take all that into account also. Right? You know, that's one of the ways it's sensitive to the evolution of the universe, right? Because the cosmological constant, for example, the current cosmological constant is so small that it played no role in the early universe, right? But it plays a role in determining how the path of the light from the CMB, that last scattering surface to today, right? So that also enters the final spectrum that you see.
Have we inserted cosmological redshift here? We have not. That has to be inserted separately. So if I'm looking at delta t by t, for instance.
Yes.
By looking at
yeah, that has to be separately. Right? That is part of the thing that it has to travel from there to here. Right? Cosmological redshift will be included in that part of the data, right? So that part we are not going to discuss, but that's a standard physics, right? We have some cosmological space-time, and we are basically the light is traveling from there to here.
That is some background effect that there has been some like expansion.
Well, that is background effect, but there may also be part of fluctuation there, right? Because imagine that it was completely uniform at the CMB sky, right? But later on, those perturbations evolved into inhomogeneities, and so the way the light will travel along various directions. So have additional fluctuations, right? Caused just by these late time perturbations. Right? So those also have to be taken into account.
Right. But the relative redshift between some point and some other point, that is already, that has to be considered.
Yeah, exactly. So that information, right, the gravitational potential at that point is encoded in chi.
But not the overall redshift.
Overall redshift will be included in the not in chi but in the evolution from there to here, right? Because you are now right now calculating delta t over t at the last scattering time, right? That so you will not see, for example, what is the 2.73 fluctuation, but that 3000 Kelvin, right? Fluctuation at that scale, right? And then you have to, bring it down to 2.73 Kelvin by this redshift factor, right? So that
right. Otherwise, I would be seeing 3000. Right?
Exactly, yeah. That time it was some 3000 Kelvin, right? That's not what you are seeing today.
Right.
So that has to be taken into account after separately.
The evolutionary wise, what we are seeing is the photons go free from
Yes.
quantum. So it's just redshift 1 over lambda.
Exactly.
So other than that, do we have to worry about how the galaxies evolve, all those things?
Well, there is a large scale fluctuation, for example, right? So those fluctuations will also remain in the later time, right? So as the photon is traveling through the medium, right, those fluctuations could cause additional effects, right? So those have to be taken into account, right? Because imagine that it was a completely uniform for some reason, right? But there is density fluctuation, right? Those density fluctuations will cause later density fluctuation, right? And that will make the radiation look as if it's not homogeneous, right? Because it is traveling different kind of paths, right? So those things also have to be taken into account. So the CMB, when you actually try to feed the data, right, with some parameters, right, you have to take all those into account and then see what is the best fit parameter.
So for lambda CDM model that we have seen,
yeah,
up to what we are seeing up to last scattering, and after that there is some like the physics is involving all sort of taking how the galaxies are forming and different position, what structures will be there. All these have to be
exactly, yeah. Meaning not the details, but the large scale fluctuation, right? Okay. So what I was saying is that this chi-LM is something that this 2-point function is something that you can directly observe, right? Because you calculate chi-LM, chi-L prime, M prime, and then average. Yes.
What we are observing is the temperature. How is chi is related to temperature?
Chi is the delta T over T. Chi, I said is some physical variable, right? I didn't say what it is, right? Whatever physical variable you're interested in, which in this case is delta T over T, will have this property, right? Because this is just kinematics, right? What variable you are using is in this function f of t. So this can be observed. Okay. And this averaging, right? It's supposed to be quantum averaging, right? But we have only one universe, so you cannot do quantum averaging, right? So this averaging you should think of as averaging over different choice of z-axis, right? Because theta phi is defined only after you have chosen your z-axis, right? And xy z-axis. So you take different orientations, right? Different orientations will give different values of this chi-LM, chi-L prime, L prime. Okay, so you average over those, right? So that's the averaging we are doing here. So let's try to calculate this. Okay, chi-LM is given here. So we'll use this formula to write the 2-point function of chi-LM, chi star L prime, L prime. Then you will have okay, R I am saying setting the same for both arguments because we are looking at different angles but the same distance. And then we have to write the two-point function R K T star. This one R K prime T star star is essentially R of minus K prime T star. Yeah, because it's in position space it's real, right? So in the Fourier space, changing the conjugating means you change the sign of the momentum. And this quantity we had introduced earlier, this has a name. So let me see what we call this. I think we call this PR, right? Up to some normalization. I think this is what we call PR of K. PR of K 2 pi cube delta Q, K minus K prime. This is the scalar power spectrum. Right? This is what we calculate using inflation. So basically, the idea is that we have set it here. That sets K prime equal to K. Okay, which basically means that it will also set theta K prime phi K prime to be equal to theta K phi K. So we'll get this as integral d cube K. Let me write this as 1 over 2 pi cube K square sin theta K d theta K d phi K. Okay, so I'm just writing the K integral in the spherical polar coordinate. K prime integral is gone already, right? K prime is set equal to K after removing this. So we have PR of K, which I bring in the front. And then the rest Fk. This should have been Fk prime. Okay, to begin with. Okay, but now K prime is set equal to K, so Fk mod square 16 pi square minus I to the power L minus L prime YLM theta K phi K YL prime M prime star 1 by 2 pi q. Thank you. Integrating over, yeah, k also, yes, thank you. Now we use the fact that this object, right, because of the rotational invariance, we expect this to be a function of the magnitude of k only, right? That in fact we calculated and we found that it's a function of magnitude of k, right? Doesn't depend on it depends on omega, right? Omega is the magnitude of k. Similarly, this f of k, even though we have not calculated it, right, just by rotational invariance of the problem, right, we expect f of k to also to be dependent on the magnitude of k, right? So PR of k should be in fact PR of just the magnitude, and similarly f of k should be f of just the magnitude. So using this, we see that the theta k phi k integral now can be done setting L equal to L prime and y equal to L, m equal to m prime. So the theta k phi k integral now gives sin theta k d theta k d phi k y L m theta k phi k y L m L prime m prime star theta k phi k. So we get an integral of this form. And this one, I think with the normalization that I have chosen is just delta L prime delta m prime. Is it clear? So this gives you chi Lm chi L prime m prime as integral dk. Okay, let me write the factor. So this 1 over 2 pi cube is 1 over 8 pi cube, and there is 16 pi square, right? So that gives you 2 over pi. Pardon? What? This one? Yes, star. Thank you. Yeah. Spherical symmetry. Okay. PR of k was the 2-point function of r of k r star of k prime, right? And that we had seen already is a function of mod k, where it depended on k only through omega, right? Okay. So that's not surprising because the background is rotational invariant, right? So physical quantities should be invariant under rotation, right? The fluctuations may be not rotational non-invariant, but when you calculate the expectation value, it should be rotational invariant, right? Okay, so that was the reason why this was a function of mod k only, omega only. And now I'm saying that this f of k also has a similar feature, that it shouldn't depend on the magnitude of k. Otherwise, it will mean that in different direction, see, the fluctuations are already dependent on k. That is true, right? But that has been separated already, right, in the form of r of k. Okay. After that, you are just doing a analysis based on the background, right? This function that relates the late time fluctuations to early time fluctuations is just determining the background, right? Because it's a linear set of linear differential equations. The coefficients are determined purely from the background, and the background is rotational invariant, right? So we expect that this f of k, right, whatever physical quantity you may be interested in, right, this f of k should be independent of k, of the direction of k, right? That's the input we are using here. Okay, later on we will calculate this f of k, right, for the specific case of delta t over t. But we have already seen, for example, phi b, right? When you try to relate phi b with Ri, right, it doesn't depend on the direction of the momentum. Right? In that case, it just so happens that it doesn't even depend on the magnitude of the momentum. Okay? But that is an extra input as the time evolution, right? For example, when you are making a transition from the radiation to matter dominated, phi b has to change from half hour to 3/5 hour, right? That time evolution is will depend on the momentum, magnitude of the momentum, because k square enters the differential equation, right? So it will depend on the magnitude of the momentum, but not on the direction of the momentum, because the differential equation contains only k square, not k as such. Okay? So that's the consequence of rotational invariance, that the transfer. So these are what are called transfer functions, that we transfer a fluctuation in Ri to fluctuation in whatever you are interested in. Okay? So there is a function that relates that to, and that function is determined by the background geometry, right? Not by the fluctuations themselves. So that should be rotational invariant. Is that point clear? Okay, so here we get 2 over pi delta LL prime delta MM prime, and then PR of k. Sorry, this is inside the integral. Integral k square dk PR of k fk mod square. Pardon? Yes, fk is only a function of magnitude. Thank you. Fk square. Yeah, otherwise it will not make sense, right? Because here I am only doing it to integration over the magnitude, right? Theta k phi k integral I have separated out. So this is the final formula, right? That this is what you calculate. Here is what you calculate. Right? This is also something that you have to calculate, depending on what you are interested in. And this is something measured. Okay, and so this is the way you relate the measurement to what we had calculated, right? So that's the reason why the fluctuations in, if you believe in inflation, right? If you believe that the perturbation was produced by inflation, then knowing the cosmic microwave background fluctuation, you can directly find information about this PR, right? Which you had seen is related to the various parameters during inflation, right? It had something like phi bar dot square, h square, etc. We can also write it in terms of the delta S. This we had written PR, if you recall, we had identified a parameter. This was given by, let me put the normalization correctly. Two pi square over k cube delta S. Right? That was the definition of delta S. Delta S square. Okay, so if you use that, we get 2 over pi. Pi square we can take outside, so it becomes 4 pi. The other point to emphasize here is that if we take large L, then JL of KR is peak around K KR equal to L. Okay, so which means K of or L over R. Okay, this is a property of the Bessel function. Okay, that it's peaked around KR equal to L. And so you see that what it does is that it picks up delta S, okay, at L over R. Right? And this is the sense that intuitively we had said the large K should compare to should translate to large L. Right? And this is what we see here, right? That K is this function, the integrand is peaked around K equal to L over R. So this integral will basically pick up delta S at equal to K L over R.
So JL is peaked around
K at KR equal to L, right? So which means at K of order L over R, right? So this thing is significant only when K is of order L over R, right? So that means this integral is sensitive to delta S at a value of K, which is of order L over R, right? Pardon? Yeah, deltas are the power spectrum, right? So the large L should correspond to large K, right? The data for large L, so this is showing that if we calculate this two-point function for large L, right, that actually picks up the fluctuations at large momentum, right, or short distance. Okay, so this is why intuitively we had said it was clear that should be happen, right? Because large L is smaller angle, so smaller separation, that should be larger K, right? Here we see it explicitly how it happens in this formula. Okay, so this is as much as I'll say about relating what you have calculated to what you observe, right? Two-point function. As I said, this f of k discussion will postpone for now. Yeah, that will be the last topic of the course. So what we will discuss now is a different topic, the origin of polarization. Right. So today, let me just give you the physical understanding of how polarization is related to fluctuations, and then tomorrow I'll complete that. I'll not, as I said, I'll not give any derivation. I'll just state the results. Right. But today I'll try to intuitively explain why polarization is related to fluctuations. So let's suppose that we have a scattering of a photon. This is gamma and this is an electron. Okay, you can think of these electrons as the gammas have energy small compared to the electron rest mass, right, at the time of CMB. So you can just think of this as static objects, right? Photons are bouncing off the electron. So let's suppose that you have a photon that bounces off an electron. So it comes with some momentum q, so q prime, and goes out with some momentum q. Okay. And we are sitting here, eventually observing this CMB photon. Right? So q, the final q, is up to us to adjust. Right? That is the direction of q, because that is what you observe. Right? You observe a particular direction and a particular energy of the photon. Right? So the final q is fixed, but q prime can be anything. We don't know before the last scattering which direction it came from, right, or which momentum it was carrying. Right? So that's arbitrary. Now we need to know something about the cross section of this process, okay? and the only thing that we need to know is how it depends on polarization. So let's suppose that this carries polarization epsilon prime, and this carries polarization epsilon. Then the statement is that the cross section is proportional to epsilon prime epsilon square. Let me write mod square. If you want to use circularly polarized lights, then this will be circular. This will have circular polarization. But okay, I mean, otherwise we'll use linear polarization. So this complication will not be there. So epsilon prime dot epsilon mod square. Right? This is the way the cross section depends on the polarizations. And it basically follows from this that even if the initial photon was unpolarized, right? Imagine that it was a mixed state with equal mixture of the two polarizations, two transverse polarizations. But what you see is that the final scattered object, right, can still be polarized, right? Because depending on epsilon, right? For some epsilon the cross section may be higher, for some epsilon the cross section may be lower. Is that clear? So an unpolarized light, right, scattered from an electron can give rise to polarized light, right? If you fix the directions of incidence. Can I repeat it? Okay. So the statement, I'll explain it with an example, right? But the statement is that even if this was unpolarized, right? Imagine that it has two polarizations, both are equally likely, right? So the incoming beam has a density matrix, right, where it's equally likely to have either the first one of the transverse polarizations, either of the transverse polarizations. But for these two transverse polarizations, right, if you fix epsilon, right, the scattering probabilities are different, right, because it depends on this epsilon dot epsilon prime square, right. So it may happen that even though the initial state was unpolarized, right, it was an equal mixture of the two polarizations, the final state may not have equal mixture of two polarizations, right. It may be polarized, right. So that's the claim, that the unpolarized light can get polarized by scattering.
So unpolarized means the state is in some density matrix.
Yes.
Left, right, or something. And polarized means it's an impure state.
Well, it does. It means that the density matrix is not identity. That it has some extra contribution from one state rather than another state. Right? Unpolarized will be how the density matrix is identity. Right? And there it doesn't matter what basis you choose, right? It always remains identity. Polarized means it's not identity. Okay. So let's consider the extreme example. But imagine that the initial photon came like this, Q prime, and the final photon Q was orthogonal. So this is ours.
This is not a full Feynman diagram.
No. It's not a Feynman diagram. I'm just drawing the path of the photon. Right? But this result comes from Feynman diagram. That if you do the Feynman diagram calculation at low energy, you find that there is a epsilon prime dot epsilon mod square that comes in the expression for the cross section.
This is not just the spin sum thing that we do when we compute these S matrix. It's some over polarization.
Yeah, that is if you want the total cross section, right? Here you are not summing over polarization. We are looking for the S matrix for a given polarization. Right? You don't have to sum over polarizations in an S matrix, right? Because S matrix, the cross section, you can talk about cross section for a given polarization, right? What is the probability of producing one polarization versus other?
Yes. But this is not done. Everything unpolarized light is coming.
Yeah. So what is special about here is that the initial state normally we take as a pure state, right? Here you are saying that let's suppose the initial state is unpolarized, so it's a mixed state, right? So to calculate this, you have to first calculate the cross section for individual polarizations and then average, right? Okay, so this is the case where the initial, so this direction is fixed, right? As I say, we look in a particular direction in sky. So Q, it's up to us to fix, right? We look at some particular direction with some particular energy, the photon. Q prime can be from anywhere. Let's consider the case where Q prime was perpendicular to the direction of incidence, right? So let's suppose that this is Z and this is X. Okay. Then epsilon prime could be either along Z direction or along Y direction. And epsilon can be along X direction okay. Now you see, suppose you choose epsilon, particular epsilon, which is along X direction, right? Then epsilon dot epsilon prime will always be 0. Because epsilon prime can only be along the Z or Y direction, right? Polarizations are transverse to a direction of motion, right? So if we choose epsilon to be along X direction, right, then this is always 0, right? So independently of what polarization you had to begin with, right, there will be no probability of producing a photon with polarization along the X direction. On the other hand, if we choose epsilon to be a polarization along the Y direction, then we may get a non-zero result, because the initial one, when the initial one is along the Y direction, you will get a non-zero inner product and you will get a non-zero result. Right? So an unpolarized beam, right, which could carry polarization either in the Y or Z direction initially, okay, will produce a polarized beam where it carries polarization only along the Y direction. Right? This kind of scattering can never produce a photon whose polarization is along the X direction.
But why can't I observe X polarized light here?
Yeah, then imagine that you are trying to look for an X polarized light, right? Then you have to calculate this, right? Epsilon is along the X direction, right? The two choices of epsilon prime are one along the Z direction, one along the Y direction.
Right? But if it's also, so epsilon is along X direction.
Yeah, suppose epsilon is along the X. You have chosen epsilon to be along the X direction, right? No, because epsilon prime has to be transverse to the direction of motion.
Yeah, but epsilon prime is the observed light.
So no, epsilon is the observed light.
Oh, okay.
Yeah, epsilon prime is the incident light.
Right. So epsilon prime is
Y or Z. Observed light, right, is what you are seeing. And suppose you want to decide, we decide that we want to look for the X polarization of photon, right? We will never see such photons, right, from this kind of incident photon. Is that point clear?
Can I see a combination of what I am looking for plus some X or Z combination?
Suppose you look, I mean, polarization measurement means that you look for photons of a given polarization, right? We want to know how many of the photons have these polarizations and how many has the other polarization, right? So you need to observe the polarization of the photon, right? And in this case, if you had an experiment sitting here and measuring the polarization of the photon, you will find that it's always X polarized. Sorry, it's always Y polarized, right? There is no X polarization in the photon, right? And that's what we call the polarized photon. That all photons, I mean, for such experiments, for such events, all photons that come and reach us will be Y polarized. Is this point clear? But the point is, of course, this is not the situation that we have, right, in cosmology. In cosmology, this incident photon can be from any direction, right? We don't, I mean, we cannot fix which direction it came from. And if we average over all such directions, right, and assume that there is absolute isotropy, right, photons from all directions are coming with same probability, with same of different polarizations, then of course this effect will go away. Okay, because there is no preferred direction anyway, right? As long as there is complete isotropy. But because of the fluctuations, right, some small amount of anisotropy may be produced, right? When we said that it is true that the universe is by large on the average scale homogeneous and isotropic. But the main idea of fluctuations is that that is not completely true, right? The fluctuations are not homogeneous and isotropic, right? So locally, what may happen is that there is an anisotropy, right? Because of the fluctuations, there may be anisotropy produced in the background, right? Around this point, right, things may not look completely isotropic. There is an anisotropy produced basically by, say, the metric fluctuation, right? The metric in different directions may be different. And so because of those anisotropies, right, there may be a residual effect which polarizes this light. In a different region, the anisotropy may be in opposite direction, right? That's what means by fluctuation. On the average, it is uniform. Okay. So you may see some polarization here, some other polarization in another direction.
Here you're explaining some electron.
Yes.
But the CMB,
I think the low energy, right? I mean, this is low energy data. So electron and proton will basically give the same result.
yeah, but in reality, we're talking about this electromagnetic thing interacting with gravitational fluctuation.
No, gravitational fluctuation is producing the anisotropy, right? The scattering is from electrons. The last scattering that we see, right, is either from an electron or proton, right? But the gravity produces a local anisotropy, so that the photons coming from different directions are not coming with equal probability, right? That imagine that for this anisotropy, it was more preferable that photons are coming from this direction, right? Then this will polarize this light, right? So you have to so it requires some work. You have to convert the fluctuations that you have found into fluctuations of polarization, right? That requires detailed analysis of what kind of environment fluctuation we have and what its effect is on the polarization. Okay? But the physics is essentially the same. This, right? The fact that if you have a specific direction of incidence, then you have polarized light, right? So if the direction of incidence is not specific, but it's not completely isotropic, right? Then also you expect a small residual polarization, right? If it's coming, say, preferential from this direction, right, then it will be the X polarizations will be preferentially absent. Right? So it will be a little more, it will have a little more Y polarization than X polarization. So if you now measure the 2-point function of polarizations, right? How the polarizations are correlated. That can be translated to 2-point functions of the various fluctuations that you have found. Okay. The actual work will involve studying in detail this change in geometry, how the isotropy affects the CMB polarization and so on. But this is the main physical input, right? How polarizations are affected by fluctuations. Is this clear? So next time I'll just write down the formula, right? Precisely what correlation function in the polarization is sensitive to tensor fluctuations, right? Without proving it, but proving it will require basically this analysis, that you have to first understand what the tensor fluctuations produce, what kind of anisotropy the tensor fluctuations produce in the immediate vicinity of a particular space-time point, and then study its effect on the anisotropy, on the polarization. Is this clear?
Also, this kind of subhorizon, superhorizon kind of.
Yeah, that is how HS is, right? We saw the evolution of H, right? HS, it remains constant super horizon, but once it goes half horizon, again there is an oscillation. Right? So the differential equation has to be solved.
So similar thing will be there in the polarization.
Exactly. But for polarization, you have not even observed the polarization 2-point function, right? So the look for these fluctuations is quite way off. But we do expect that if we can observe, right, it will have exactly the similar kind of fluctuation, right? Because sub-horizon ones will have the oscillation of the kind that we saw. It's the same kind of differential equation we got, right, for HS. Okay, so I think I'll stop today and then we'll continue tomorrow.
When you say about the helium or hydrogen fraction, it just means the nucleus and this is that functionally, right?
Yes, exactly. Yeah, not after.
Not and there's not specifically this helium atoms or hydrogen atoms.
So, meaning whatever is produced at the time of it.
Yeah, whatever because that will remain later on combined.
Exactly. Yeah. Meaning later on, of course, the stars can convert hydrogen to helium, but we are not supposed to take care of it.
Not that